So welcome to this TILOS seminar. I'm Henrik Christensen, one of the co-PIs. And I'm very happy to sort of talk about this. We talked about this for a while, that Nicklas should come and talk about big in robotics. And big here has so many different dimensions. It's going to talk about a paper that at the time when it was submitted had 151 co-authors. Had we done it today, would have had 279 co-authors. It sort of involved terabytes and terabytes of data on this, and it just won Best Paper Award at a conference in Tokyo or Yokohama. So it's big in so many different dimensions. We thought this would be cool, real world example of big, and how can we use this in TILOS when we talk about sort of optimization and scale. Nicklas is a fellow Dane, got his initial education at the Technical University in Denmark, came over here and is now a PhD student with Hao and with Xiaowang. And he's talking about something that was actually a joint effort with Quan, who was one of my former students. So there's all sort of entanglements here. So Nicklas, we're looking forward to this. It's all yours.
Thank you so much for the introduction. Yeah, so I'll be talking about some of the things that are happening in the robotics community right now. There's a lot of efforts in scaling, which is what we've seen in language and vision, and we're now increasingly seeing also large data sets and models in robotics. Yes, if you have any questions, just feel free to interrupt. All right, so we've seen a lot of progress in AI agents, quote unquote, in the digital world in the last few years. So there's conversational agents like ChatGPT that you can interact with. There's generative models that you can prompt with a language, and then it can generate images for us. And there's increasingly many multimodal models that you can prompt with either images or text, and you can generate high fidelity 3D models for you. So we've seen a lot of progress on interaction in the digital world. And some of the ingredients for making this a success are listed here. So diverse data, we need lots of data, which is often scraped from the internet. We need some kind of architecture, which is a neural network that is scalable, meaning that as you increase the number of parameters of the model and you increase the size of the data set, you get a better model out of it. And then in order to train these models on these data sets, we need some kind of objective. And it's important here that the objective is general enough that it captures all of the different tasks that we want to do downstream. So in the case of language, this would be next word or next token prediction. And in case of images, there are variations of this objective that are adapted to those modalities. Now, let's talk about agents for the physical world. There's a lot of things that are shared. Robots need language. They will need perception, but they also need actions. So robots need to interact with the environment, which is not something that digital agents have to deal with. And there's a lot of complexity and nuance in interacting with the physical world. So it turns out that language and vision is not sufficient for robotics alone. We need this extra modality. The problem here is that real robot data is extremely scarce. There is no internet of robotics that we can just scrape and use it to train our models. So this is a significant challenge in developing physical agents. So I want to first start out with the progress that's happened in language and vision. We have seen a lot of progress in increasingly big models, and there are also a lot of the successes because the data sets are really large. This started about 10 years ago with ImageNet, which is a big data set of images that are scraped from the internet. We also have big language data sets like Common Crawl and Wikipedia that are also scraped from the internet. And we also have a lot of multimodal data sets now that are mixtures of images and text. The nice thing about these data sets is that they're naturally occurring. They already exist out there, and we generate data passively just by interacting in the internet. And we're able to scrape all of that data. But this is not something that we have in the case of robotics. There's no internet of robotics. There's no way to just get this data stream passively. So the project that I'm gonna discuss here started kind of as an observation of what's happening in the other fields and how we can build this sort of like passive data stream in robotics as well. So if we go back to about last summer, there were a few big robotics data sets out there, but they're kind of scattered. So these are some of the names: RoboNet, Bridge, RoboTurk, and QTOpt that are developed by academics and industry and released to the public. And these are all quite diverse in terms of the tasks that the robots were doing. It would be usually tabletop settings where robots are interacting with everyday objects. But they're pretty limited in diversity, meaning that it's only collected by this single institution. The project here is kind of a community effort in pooling all the existing data sets that exist in academia. There's a lot of academic labs, ourselves including, that did have a lot of robotics data from our own lab environments that we have collected but didn't release because there was no point in releasing a small data set of our specific robot doing very specific tasks in our lab. But as a community effort, if everybody pools all of their resources together, we suddenly have a data set that is much more diverse than any institution could do alone. If we look at some of the scaling efforts here in terms of data sets, this is again from last summer. We had about 5 data sets for this project in June. And as people started onboarding more and more data sets, the size of this entire project became much bigger. And by September, when the conference deadline was nearing, we had about 60 data sets. And I think today it's about double. And another benefit is that a lot of these other data sets are not just single robot arms in a single lab environment doing the same kind of tasks. There's a lot of diversity here in which kind of task we're doing. There's data sets that have long horizon tasks, meaning that it takes several minutes for a robot to do a task. There's interaction with soft objects like Play-Doh or like liquids. There's dexterity. So instead of having a robot arm with like 2 fingers, we have maybe dexterous hands that can do multi-finger manipulation. And there's also other modalities like tactile sensors and audio and other modalities as well. So there's a lot of opportunity for very rich and diverse representations and models trained on this data set. And the project that I'm discussing here is sort of kind of the pooling of all the existing data sets that are out there in a single format that is unified and easy to work with for people. The project here is called the Open Cross-Embodiment Dataset. These figures are from last summer, so most of them have like about double in size. I believe the dataset is now 2 million robot episodes. There is more than 20 robot embodiments, meaning different kind of robots. Most of them are commercial, some of them are not commercial. It's a collaboration effort with many different research labs across different institutions and continents. So it's many more people than myself, my collaborators. And what's most important, I think, is that there's a lot of different scenes. So when we collect data in our lab at UCSD, we have maybe 5 or 6 different scenes that we can build, like small like toy kitchens or something where the robot can interact. That limits the diversity because we're not able to generate data at the scale that we really need to get generalization. Here are some examples of what the data set looks like. There's many different embodiments. There's the Google robot, there's the Stretch. I think this one's from NYU. There's a robot in the kitchen in the bottom is from UCSD from our lab. And there's also an X-arm with a bimanual setup with 2 arms. There's many different scenes. There's a robot lab. There's more everyday kitchen environments. There's outdoor environments, and then there's tabletop manipulation as well. There's also examples of many different skills. So it's not just pick and place. There's examples of pouring liquids. There's examples of unfolding laundry. There's cable routing, which is a very high precision task. And there's also screwing, which is more industrial in nature. So very diverse data set.
Question?
Yeah.
So all the data sets are ultimately videos, or are there other inputs as well? Like
It varies quite a bit. So there is a way to filter by modalities and what is in the data. Some of them are just for perception or states. Some of them are single camera, some of them are multi-camera, some of them are multi-robot. There's also a lot of language instructions in some of the data sets. Some of them have touch, some of them have depth sensing, some of them have other auxiliary information. There's some of them have audio, I believe. So very, very diverse.
So, and there's a lot of labeling, so it's not just raw video.
Yeah, yeah. It really depends on the specific subdata set and what people already have. But it's, yeah, there's a lot of modalities in there. The goal of the project is to provide all of this data that already exists in a public and easy to work with manner. So they built a API here, some of my collaborators, that allows you to very quickly query and download data from specific subdata sets in this project. So ideally it's something that is stored somewhere in the cloud. You can work with it either streaming or you can download it all locally and work with it locally. Something that is important, which relates to your question, is that if I'm here at UCSD, I have a Franka robot and I want to train a model that can work with this Franka robot to solve some tasks that I care about. It would be convenient to have a big external data set available that I can query for, say, only the Franka data. So I don't necessarily need a big model that can work with 20 different embodiments. If I just care about Franka data, I can do that. And similarly, you can also filter by the modalities. So say I only want data that has a wrist camera, or data that has language instructions, or tactile feedback, or something else. So there's a nice API for filtering and only downloading the data that you care about. The problem here with very diverse data is also there's a lot of new challenges that we have not really faced before. This is kind of the first effort in actually pooling resources across so many robots and training models across locations. So there's a lot of infrastructure problems, there's a lot of data management issues, and there's just a lot of diversity in the tasks that individual labs actually care about. These are some of the images of the different lab setups. Now, aside from the data contributions themselves, the key research question that we ask in this project is whether it actually all matters. People have been training specialized models to solve very specialized tasks in robotics for a very long time. The question here is whether we can get the same kind of generalist models that we have in language and vision, in the sense that, is it better to train a model on all of the robots that we have seen than training individual models for each robot? Because if this is not true, then there's no point in having this big data set. So there are some experiments that I will go over. There are some modeling assumptions right now to make the experimental setup more feasible. So one of them is that we filter the data by how many arms the robot has. So right now we only consider a single robot arm, parallel jaw, 2-finger grippers, a very simplified setup. And there's much more robot diversity out there, but this is in order to make things feasible. Even though we do limit the data they would work with, you still see that there's a lot of variety in what the tasks and settings look like. And there's still different robots, it's just all single arm. We trained 2 different models. These are both RT transformers, originally developed by Google. RT1 here is the first iteration of the model. It's a transformer that is trained on robot data, so it takes text as input, which is a language instruction of what the task is about, and then a sequence of images. And then it outputs directly actions to execute on the robot. And then there's also RT2, which is a bigger model that is first pre-trained on a big language and vision data set, so external data, and then is fine-tuned on robotics data. So these are the 2 settings. And the actions here are discretized and the finger positions, just to make things simpler. So there is a finite number of actions that each robot can take. And we just directly output gripper, opening and closing actions, velocity, and rotation. Another simplifying assumption is that each of these robots in each of the different labs actually were recorded and run at different frequencies. So we don't do anything special to deal with that. So we don't unify the frequency. We just deal with different data sets having different frequencies. And that means that the model that we train will infer the frequency based on the data that it has seen, which also makes it harder to transfer across different robot environments. But at least that's what we have for now. So the way that the models are evaluated is that all the data is stored somewhere locally in, let's say, lab A. We train RT1 and RT2 models in lab A. And then for the RT1 model, we send the checkpoints to each of the different labs that we want to evaluate this checkpoint in. And this can be done by sending the checkpoint over the net and then running inference locally, because the model is still fairly small. It's about 50 million parameters. For RT2, the model is actually too big for most labs to run it locally. So we set up a API, remote API, for labs to send images and language instructions in real time, and then for the robot model in the cloud to respond with which actions to take. So there is some latency, but because everything is kind of like manipulation and still fairly low frequencies, things work out fine. And so these are some of the students that have been doing the actual robot experiments. These are in 6 different universities. These are some of the lab settings that we've been doing evaluation experiments in. So there's a setup at Berkeley, there's one at Stanford, there's one at USC, there's another one at Berkeley, then there's one in Freiburg, and then at NYU. And so all of these students were sent the checkpoints for the API, and they would run evaluation in their specific lab environment. And now I mentioned that all of these data sets existed previously to this project. And that's because all of these data sets were collected and used for some prior publications. So all of these labs already had the data sets available, and they already had models for the purposes of their study that they had evaluated on in these lab settings. And so what you see here on the right side, the bars here, is the success rate across all of the different lab environments with the original members that were developed for those specific data sets. And so that's the one on the left here. And then the one in the middle is the success rate of an RT1 model that is trained only on data from each of those individual labs. So with only the data available for a single robot in a single lab, the RT1 and the original method is doing approximately the same in terms of performance. But then we can go back and train another RT1 model that's exactly the same. There's no changes in size or how it's trained, except that we now train on data not only from the single robot in that lab, but also on data from all the other robots. And what's a little bit surprising is that the model that has seen more data from all the different lab environments is doing quite a bit better in terms of success rate, even when it's evaluated on the exact same tasks.
Do you know that if you actually train, still use RT1, but then increase the training set to match whatever you're using for the RT1X? What would
I don't know the specifics actually. I think they did try multiple different checkpoints when training, and I'm not sure there was any big differences. But yeah, it's very limited amount of tuning that you can actually do with the scale. Yeah, so that was experiment with the RT1, the small model. Next, I'll discuss experiments on the RT2 model, which is quite a bit bigger. What is the number of trials run? I believe here there's about 3,600 evaluation trials. And so you can imagine, so these are across all the different robots in the different labs. It has quite a lot of different tasks, different object positions, and also different objects, and also different language instructions. So it's fairly large scale evaluation. This is also something that we'll come back to, but actually takes a lot of time and human effort to do reliable evaluation. Yeah, so for the RT2 model, it's trained not just on robotics data, it's also trained on external vision and language data. So it's a pre-trained VLM, which is trained on like large-scale multimodal data sets from the internet, and then it's fine-tuned on robotics data. So there's an interesting question here in whether, when you already have all of the internet information available, does adding more data from other robots actually matter? Or is it enough with all the internet information in order to solve tasks in a single lab environment? So in order to set up a evaluation on this, researchers at Google, they set up a spatial reasoning evaluation. So the Google robot here is trained on these tabletop environments, and they have a fairly principled way of collecting data. So it's very easy to say which kind of evaluations are in the training data and which ones are not. And in these examples here, for example, the one on the left, there are variations in where to move an object. So you can give a language instruction that says move apple between Coke and cup, which might be in the training data. And then there's some other variations that are not in the training data, like moving it between the cup and the sponge. So in this way, you get a very principled way of understanding whether the model actually generalizes to new spatial locations that are not seen in the training data. What you see on the left here is the success rate of RT2, which is trained on the out-of-domain data, the internet data, and then fine-tuned on a single robotic embodiment. And then the RT2X here is the same base VLM that is fine-tuned on robot data from all of the robots in the data set. And again, here we see that even with access to all of the internet, still having more robotics data is very, very beneficial for generalization in a single robot environment. And there's some example videos here on the right where you see the robot is asked to put apple on the cloth or near the cloth, and it seems to be able to understand like the spatial relations between these objects. So just to summarize this project, it's a big data set that is a collaboration between many, many different labs. There's a lot of robot embodiments in there, many, many different seeds. And there's also, again, 2 million plus robot episodes available right now. And it's increasing every month. The data set is open source. It's very, very easy to use. There's a simple API. And as long as you have the storage for it, you can easily download the entire data set and work with it. We've also shown that using this data set is actually useful for robotics. Even with big VLMs that have seen external data, still having more robot diversity does improve downstream performance. I want to conclude discussing this project about just discussing a little bit about the limitations of the current setup and the data set. And I think the first point to make is that the data set is very, very diverse, but it's not diverse enough. It's still very lab environment-esque in that a lot of them are table manipulation or toy kitchen environments in lab environments. And in order to really get generalization and to solve real problems that people care about, we need much more diverse environments. So we need to collect data in households and factories and other like everyday environments where robots might be present in the future. There's also a lot of diversity in embodiments, but there's still not a lot of mobile manipulation robots in there. There's no humanoids as far as I know in the data set right now. There's also no drones. So these are also robot embodiments that would be useful to include in the future. There's also a point to be made that a lot of the tasks are not super realistic. A lot of the environments are kind of these tabletop environments with neatly placed cameras. A lot of the objects are rigid objects. There are a lot of plastic fruits in there. And ideally, we want also robot data sets where they're a little bit more realistic. Like UAVs, drones, flying drones. Not included in this project, at least when the slide was made, and I don't know actually about today. Yes, yes.
But it's very expensive too.
Yeah, the initial focus of the project was to focus on these single static manipulators, and I think now it's increasingly expanding out to other embodiments. I think of it mostly as just a proof of concept that sharing all this data does make sense, and there's some benefit to that. And now I think we're slowly expanding the kind of data that we have. Yeah, it's really about getting a critical mass of data shared. And
in this data set, there are other data sets, right? Which, or it is like basically no freely available experience. I've been picking up to.
I think not at that scale. It's more at this scale what we have. So that's easy to just have one drone, one scenario. But getting all of these scenarios and all of these variations in to provide, so you really want to know, could you build a generative model that would generalize across scenarios, robots? Or that's what makes it hard. If you're just flying in an urban environment, it would be hard to talk about generalization.
Presumably, there are probably lots of private data. Like
Oh,
Amazon,
oh,
I'm sure.
yeah.
Check that.
Yeah, and I don't know if you look at the military drones, the police in Chula Vista flies drones every day. If you call 911 in Chula Vista, they're not gonna send a police cruiser, they're gonna send a drone. And they've done this 19,000 times. The average time of arrival is less than 100 seconds. So within 100 seconds of you diving on that drone is hovering over where you are, providing downward imagery to the 911 operator so they can have an appropriate response. So an ambulance, it's a fire truck, it's a police cruiser that should come. So they might have data, that's something, I don't know.
yeah, sure. I should also say that the problem is not that the data doesn't exist, it's that it's not being shared. And I think that's also the case for a lot of the manipulation data set that is included here. It's already data that existed. It was already collected maybe years ago in robotic lab environments. It's just that there was no incentive to share, and I think that is starting to change.
But and then I think for the RT2, it's also that there is an API service. So through a Google Colab, you can actually access it. There is, because it's so big that most of us don't have the computing resources.
Yes. So the last point I think I wanted to make about the data is that also there is no simulation data set there. I think there's a couple now, but it's really just real robotics data. And simulation has come a long way and does have a lot of potential for creating very, very diverse and rich data sets. There's not something that is exploited right now, but I think in the future, we might interleave real and simulated data more. There's also a few limitations in the current setup. I mentioned some of these already, but the RTX models that are trained and evaluated here are right now these single arm robots. There is not a lot of flexibility in the kind of inputs. So the models assume actually that even if there's more cameras available, right now we just use one. There's also other modalities like depth sensing and tactile and audio that is not being used, although it's actually in the data set. So there's a need to develop models that can consume this kind of flexible data, where sometimes you might have sensors available and sometimes you might not. There's also a need for models that are more flexible in which kind of goals that you provide. Sometimes if you want to teach a robot to do a specific task, sometimes it's easier to describe in language. Sometimes it's easier to just show the robot what to do. And sometimes you just want to provide a goal image. So we need models that can handle all of these different kind of task specifications. And also because everything right now is single arm, we just use end effector positions in all the experiments. But especially with other robot modalities that not necessarily are specified in this way, it's also useful to have action spaces that are joint space or base movement, and this is a mobile manipulator or bimanual or like humanoid. We need models that can work with all of these robots in the native action spaces to those embodiments. And the last point here is that the fine tuning is actually very, very expensive for the RT2 model, which is not something that academic labs can do. And I think in the future, if you want robots to be useful in academic settings, we also need to make the fine tuning feasible to do in academic settings. So compute is still a big bottleneck. One last point also that is kind of like ongoing or future work is that this project has really been about sharing and pooling data, but also evaluation is still a big bottleneck. So the evaluation for this paper took many, many hours and many, many people. And ideally, in the future, we would have a more automated and reliable way to evaluate these big checkpoints. So much like we have been sharing data recently, also pooling different benchmarks from different labs would be very interesting. There's a lot of simulation environments that different labs have built. My own collaborators in my own lab have been building some simulation environments. And there's also a lot of real standardized benchmarks and real robots that are being used to evaluate robots in sort of like very constrained lab settings. But it would be nice to have more like a pooled effort also in evaluating new models. Yeah, just to say again that this is by no means my work. This is a collaboration with many, many other people. And this screenshot was from one of the early meetings in the project, almost a year ago. And there's a lot of people that have been involved. The publication here that came out of this project was
Mostly physics now.
So,
Astrophysics.
so we broke the manuscript system. Literally, they can, their sort of paper set from IEEE cannot take this many authors.
We only accept 64 authors.
151, I think.
Yeah, something like that.
151 that's on this stuff. And now if we were writing it today, it would be 279.
It's grown by almost 200 people in a year. So it's a big, big effort, and it continues to grow still. And yeah, so this is a picture from Japan last week, as Henrik mentioned, where the project also won the best conference paper. And this is again just a small number of the authors that contributed to the data, but nonetheless, yeah, I think that's it. If you have robot data or you're interested in accessing the data, it's all available online. There's a link here. There's also quite detailed instructions. There's collabs, as Henrik mentioned, where you can interact with the big models that were trained. And also, yeah, if you have any other questions, just feel free to reach out. This is very much an ongoing project. I don't think it's finished here, and hopefully the community will keep growing.
But it's also interesting from this that this has led to at least 3 spin-outs from Google DeepMind. So 3 different sort of groups have spun out of DeepMind and collectively picked up checks for $400 million. So there's clearly money to be found in large models.
Yeah, so that's a great point where I think we have.
So those are also co-authors of those.
Sorry?
The one who have this now, so they're also co-authors of this paper. They're involved in this work.
Yeah, they're co-authors. So all of them are. So yes, I'm still trying to understand the relationship between Google IP and spin out IP, and I think people are just like not paying attention. But I think it's very surprising that just the model is worth that much.
Yeah, I think we have enough initial evidence now that the recipe is working for scaling. And right now it's just about collecting data, quality data, and diverse data. So I think that's what a lot of startups are realizing.
And getting real life computers. If you Google DeepMind, you can allocate a file for this. Most of us don't. It would have taken us years if we've done it.
Yeah.
I think it will be like ChatGPT once you have an update.
That's the hope. I don't think we have demonstrated yet that it actually, it will be demonstrated sort of what, because you're getting significant generalization. And it's much better than the individual data. But as Nick pointed out, there's a lot of limitations left to sort of,
You can do very well in a constrained number of diverse settings. And I think it seems that the experiments are indicating that the key is just more data in a lot of cases. So yeah, that's quite interesting.
That's what we see in many domains. Now we have to
did you have more?
Yes, I have a few more slides. Yeah, this is concluding the Open X-Embodiment project. I'll just show a couple of slides of some of the work that we're doing here at UCSD along the same directions. I'm personally working on reinforcement learning and world models, and they address some of the limitations of these current RTX models. And one of the biggest things that I've not discussed in the previous slides is that RTX models require demonstrations. The entire data set almost is teleoperated. There's lots and lots of humans that have teleoperated all of these robots and collected data. And the RTX models assume that those demonstrations are reliable in terms of the actions to take. So the models don't learn from failures right now. They're all filtered out during training. So yeah, it's useful to build models that can also learn from the failures, especially when you enter like deployment settings where you can have a robot passively collect data and you learn not just from the successes. So one framework for doing that is reinforcement learning. It's a framework for iterative refinement of behaviors. You might start with a random policy, or you might start with, say, an RTX model, and then you can iteratively refine it by interacting with the environment and collecting more and more data. And these are examples of some of the things that we've done in the lab, where we've been able to train RL policies on real robots with just a few hours of interaction. The problem with reinforcement learning is that it's mostly limited to a single policies per task. So they're very, very specialized models. We don't really have the kind of generalization of these bigger models. And a lot of that is because RL algorithms traditionally don't really scale. So if you take an RL algorithm and you give it more data or make the model bigger, you don't necessarily get better performance, which is what we're used to seeing in language and vision. And that is partly because the algorithms are very, very brittle and they're very difficult to tune. So there's a lot of effort in actually making these algorithms work. And so like my general research direction here is whether we can build RL algorithms that have the same kind of scalable and robust behaviors as other big foundation models. Robust here means that it's not sensitive to high parameters. So if you download the code and you download your data, ideally you should get a good model out of it. And also, when you increase the size of the data set and number of parameters in this model that you train with RL, you should also get a more capable model. And so one such publication that we did this year at iClear is evaluating world models and making them scale to much bigger data sets than what have been considered before in reinforcement learning. So what is a world model? A world model is very similar to the kind of transformers that are trained in other domains. It's a model of the world that's not really tied to a specific task. It's just predicting, given the current state of the world and an action, what will happen in the future. The idea here is that you can train world models on very, very big data sets of lots of different robots doing stuff in environments, and then you can learn kind of an approximation that you can simulate and plan actions that you would take in the future. I'm not going to go into detail with the method, but the way that it works is that you can prompt the model with the current environment. So say you have a simulated dog, you encode it into some kind of latent representation, then condition on a sequence of actions that you want to take, you can simulate what would happen in the future. And then for each task that we want to solve, there's some kind of cost estimate or return estimate of how well this sequence of actions would obey the task that we want to achieve. And we can simply like just sample a lot of different action trajectories and pick the best one. Now, this could be used in an online RL setting where we start with a very poor quality data set of a dog not being able to run. And we iteratively refine this policy, the world model, and end up with a policy that now in the end can run at least reasonably well. I don't think this would transfer to a real dog, but it's able to run. And we're able to train these models on many different tasks, both individually, and we've also trained models on all of these tasks jointly. So this is all in simulation, but we're able to train a single model that can control all of these different robot embodiments and all of these tasks. And what's interesting is here, so TDMC2 here is the second version of our work. We also have a TDMC1, which is a previous version, which is also a well model. And if you increase the number of parameters of a traditional RL algorithm, you get something like the blue curve here. So y-axis here is that normalized score on the big multi-task data set of about 100 tasks. And the x-axis here is model parameters in millions or billions. And what you see here is that when you increase the number of parameters of a traditional RL algorithm, you actually get worse and worse performance. And this is mostly because of optimization issues. We do address those issues, and with some implementation level tricks, we're able to get an algorithm now that can scale much more reliably. So now with a bigger data set and bigger models, we can actually also get better performance. We're able to scale to about 300 million parameters, which is about 300 times bigger than most other algorithms out there. And it turns out that if you fit like a curve aligned to this plot, you get something that looks not linear in terms of scaling. And this is very similar to what people in language and vision have been seeing.
So it's still a lot smaller, right? Than
Yes. Yes. So this one is 300 million. The RT1 model that was trained on the open embodiment was about 10 times smaller than this. And the RT2 model is about 10 times bigger than this. So it's pretty much in line with.
This is the gradient.
I think we're getting there. Going beyond 300 million in an academic setting is very difficult.
So just make sure, so the key reason that this is now much better is because that you're using a world model behind and then using this continuous control that's somehow because of the latent space, it works better now. Is it?
Yeah, so we don't have a comparison to the RTX models here, but the main difference between these two curves is implementation, which is somewhat surprising. So they're both world models, but they're implemented in a way that is more scalable.
So we need implementation based on. So what do you mean by sorry, what do you mean by engineering?
So yes, one thing to know about training big models is that even though you have the data set, there's a lot of infrastructure issues that you face, and there's a lot of optimization challenges. That the models very often become unstable and just kind of like diverge and collapse in performance. And they tend to be very brittle to like hyperparameter tuning. So you need to tune a lot of parameters just to get something that scales reliably.
But implementation is also, if you think about it, how do you present your data set to the model? You just do it at random, there's no guarantee. So it's all open. Can you do a smart curricular-based learning and that will improve your performance?
So one thing they do, I don't know in this large language model, they have this idea of high quality data. And on that they actually do only one epoch on like this, just like the dump of all the data, do many epochs of high quality data.
Yeah, there's a lot of things like that.
But that's maybe interesting.
But I think the methodology, exactly. So the methodology plays a big role. You just do brute force. Success is not guaranteed.
Yes. Yeah, I think what's interesting here is that I don't think there's any of the implementation details here that are like, it's all stuff that people have been finding out in language and vision that these are really useful for scaling models. And we're applying some of those tools in the context of RL and seeing that it's also working there. So yeah, there's lots and lots of people working on making these trainings more reliable and more efficient. Yeah, if you're interested in RL and these like simulated environments, we also open source everything. So there's all the models that we have trained from small to big. All of the data is out there. It's about 500 million transitions in the data set. And also there's code for training and developing the models. So this is all open source. But I want to just spend 2 minutes concluding the talk and showing some very new results that we have been applying these world models to. And one of those are humanoid controlling. So humanoids are interesting because they're kind of robotic in nature. And they're very high dimensional problems, which is interesting for us learning people. They're very high dimensional observations in that they a lot of sensors on them for perception and tactile feedback. They have often cameras to see what's in front of them, and also the action space is very large because you're controlling all the joints in this humanoid. And there's another less appreciated aspect of humanoid modeling, in that often humans want humanoids to perform motions that are natural to us, whereas for a robot arm or a robot dog, I think it's less obvious to us that they would have like these kind of natural human-like motions. And so what we see here is that our TDMPC world model pre-trained on large-scale motion capture data of humans performing tasks. We have a mocap data of about, I think, 200 hours of humans doing mocap, random stuff. And we see that pre-training on these large data sets with human data actually also brings human-like policies that are much more natural. This is what you get if you train a reinforcement learning algorithm on this task. You see that it solves the task according to the specification. You actually run at the same velocity, more or less. We see that looks much less natural.
If you actually implement this in a robot, it would work, or would it just completely collapse?
No, it would work.
It would work.
Yeah.
So maybe that's okay. No?
I think if you start deploying humanoids in the real world, I think people will care increasingly that it
People
also
will freak out.
Freak out about this thing coming running down the street, you know.
Yeah, we have more examples of this, and I think it's a very general thing that reinforcement learning is really good at optimizing and learning policies that solve the task, but it's kind of over optimizing sometimes. There's one example here where it's asked to move up the stairs as fast as possible, and it learns like this kind of falling behavior. Yeah, so we do some user studies here, and we see that unsurprisingly, humans prefer humanoids that are trained on human data. It's much more natural. I want to conclude just with a video from my collaborators that have been applying very similar methods to what I just showed on real humanoids around locations in San Diego. Where here you can actually, this is a humanoid robot. You can prompt it with a YouTube video of a human dancing, and it will be able to imitate that in the real world, in real time. So yeah, my colleagues have had a lot of fun just shooting videos around San Diego. But yeah, I think the key here is just to train models that work in the real world and also are not just learning to optimize and like solve the specific tasks, but also do it in a much more expressive and human-like way.
So when the sound it actually is stable enough that it can compensate for the surface.
Yeah. They tested it on quite a lot of terrain, so concrete and sand and stuff.
So that's a lot like UCSD that people just walk by, don't need to pay attention. We must have a lot of crazy stuff going on campus.
It's surprisingly stable. The specific robot here is the Unitree H1, came out a few months ago.
But so is there a reason why it has to move the legs all the time? It's not statically stable.
It's not super stable when it's standing still. It's actually really difficult to balance standing still.
So it's not statically stable, but it's dynamically.
Yes.
Just
So yeah, there's,
A little bit of raw process.
Yeah, that's pretty impressive.
it is surprising to say. Yeah. I think one limitation here is that you see that it doesn't have hands actually. Right now it's just kind of it stops at the joints. So that's also like in the future, we want to put dexterous hands on the robot so you can actually do useful tasks with this human. Yeah, I think that's all. Just a quick announcement of all the people that have contributed. So my advisors, Sean and Hao, and also Quan and Carl and Chelsea, which has been helping with the slides for the Open Cross-embodiment project. Of course, also thank you to all the people that contributed data, and also all of my collaborators have contributed to some of these projects that were in the slides.
Thanks. I can see you have some questions in chat.
Yeah, so there's a question here on how the lower body is controlled. And so for the specific humanoid in the real world, is trained kind of a hierarchical approach. So there is a different controller that is controlling the lower body and stabilizing that. And then there is a higher upper body controller that is imitating human movements. So right now it's separate, but I think in the future it would make sense to train a single model that can do both.
Okay.
I have another question. So, I mean, earlier when you talk about the emerging skills, are there study that based on your, whatever the task you're given for the training data, what type of new skills might likely to be more easily, developed? Maybe there's some.
I think that would be interesting. It's still very underexplored, I think. The models are released, so people are welcome to study that. But it's really difficult to understand these models. Because even sometimes very, very small differences in object position can lead to quite different outcomes. So they're not super reliable still.
So there are, the only one I know off the top of my head, sort of at scale, is 2 years ago, Sony AI released, so there is this game called Gran Turismo, and people spend lives learning to be good at Gran Turismo, and there are sort of world championships, and there's all of it, so there are, especially in Japan, super famous game players. And Sony said, could we use reinforcement learning to learn that behavior? So they took 500 PlayStations and used sort of very relatively basic RL and trained it. And within a week, they've beaten the world champion. So now in the latest version of Gran Turismo, you can drive against real drivers or AI agents. And they studied with some of the very experienced drivers how the RL version is using tricks that the human players have never thought about. It's like, oh, that's a cool way of doing this. So it drives so it uses different ways of going through corners and different ways of doing overtake stuff that the human drivers have never thought about. So it's a nice paper in, I think it's Nature, with the people. So it's mainly people from UT Austin, Sony AI, and some people, the Sony people in Japan that have sort of studied what are some emerging behaviors that they have never thought of.
No, I'm just wondering that also for the first part, if you have a better understanding of those, then you can target to get more data, more useful diverse data instead of just diverse data, right? Because you know what type of data would help to fill certain skill hole to lead to a bigger space. Yeah, so.
Yeah, I think it's hard to evaluate, but I think in my experience, one of the things that are very difficult to scale is like camera positions. So even though you have a lot of diversity in the data and the tasks that you're doing, you always, at least for each lab environment, you have maybe a very limited number of camera positions that you actually collect data from. So if you just perturb the camera a little bit, you actually get much worse performance just because everything is kind of like skew towards a different viewpoint. So in order to solve that, I think you need much more data.
Or you have your model somehow can
Yeah.
handle this, whatever invariance or whatever.
Yeah.
I think you might have one more in chat.
That's the robot switch from Datasets. I'm not sure exactly which of the models that you refer to. But for the most of the first models that were trained, UCC. So like the humanoids here are, this one humanoid in the real world is controlled. So there's a fixed number of commands that they have developed, and you press a command and it will execute like a sequence or try to imitate that sequence. I think that's mostly just for practical purposes. You could download new motions from YouTube or something and those. But right now it's still like controlled by you. The actual command to the robot to do.
But Nicklas, if you had to do, so if you go back to some of the earlier ones, let's say clean up of a kitchen or something like that, could you do the sequencing of, first you remove the plate, then you do the cover, then you do, how do you task that?
Yeah, right now everything is with language with these models. So you have to provide an instruction, and then when you feel like the task is completed, you provide a new instruction, and the robot will switch over to that new task. But there's still a human in the loop in that way.
Yeah. Cool.
Yeah.
Yeah. Thanks, Nicklas. Okay, thanks.